This problem is a little different from the ones associated with this problem set. It says a small box is held in place against a rough wall by someone pushing on it with a force directed upwards at 28 degrees above the horizontal. The coefficients of static and kinetic friction between the box and the wall are zero point 0.4 and zero point 0.3 respectively. The box slides down unless the applied force has a magnitude of 13 newtons. What is the mass of the box? So I've made a picture of it or a sketch of it right here. We can see that the applied force is going up and to the right, and we know that that's angle theta is 28 degrees. If I were to draw a free body diagram of the forces acting on the box, there's going to be a force going up and to the right. I'm actually going to ignore what I just drew right here, and the reason is I want to represent those forces as components. So there's going to be the x component of the applied force and also the y component of the applied force. The weight, mg, is directed downwards, and there's also a normal force of the wall pushing back on the box. Of course, this is an electromagnetic force due to the electrons in the wall and the box. And nothing is moving as long as the applied force is sufficient and meets this threshold of 13 newtons. So since the system is not in motion, I know that the sum of the forces in both the x and direction are x and y direction are equal to 0. So I'm going to go ahead and write dynamics equations accordingly. And so therefore, the sum of the forces in the x direction is going to be the x component of the applied force minus the normal force is equal to 0. And in the y direction, I can say that the y component of the pushing force minus the weight is equal to 0. Oh, wait, and I've clearly forgotten a very important force here, and this might be where you made a mistake, so I almost fell into this trap. The box has a tendency to slide down the wall. Notice that if the applied force is small, then there's additionally going to be an upwards frictional force, and I'm glad that I left this in the recording because you can see that it almost caught me as well. And so therefore, I'm going to need to make an adjustment to what I've done here on my dynamics equation. I'm going to have to also add into it the frictional force. So the frictional force is positive, it's up because of the tendency of the box to slide down. And so the expression that I'm looking for is going to essentially be over here in the y direction because they want to know the m, the mass of the box. And so therefore I'm going to add mg to both sides. And I get the y component of the weight plus the frictional force, the y component of the applied force plus the frictional force is equal to mg. At this point, I can start making some substitutions. I can see that the applied force y component is going to be F times the sine of the angle theta, which is 28 degrees in this problem, plus mu, and I'm going to use the static coefficient of friction because the box and the wall surface are not sliding past each other yet, as long as this condition is met. So I'm going to multiply mu static times the normal force, and that's going to be equal to m times g. And again, solving for m, I'm going to divide both sides by g. This becomes f sine theta is plus mu static. And we can see this time that the expression for the normal force is going to be developed over here in the x dynamics equation. So I can say that f cosine theta is equal to the normal force. And it's that expression for the normal force which will be substituted over here in the y, not vice versa, as it usually is. So this becomes mu static times f cosine theta is equal to mg, and then I'm going to divide both sides by g. Since f is known, so f is known, theta is known, mu static is known, again f, again theta, and g is 9.8 meters per second, I can go ahead and substitute these values in. F becomes 13 newtons. I'm going to multiply that by the sine of the angle 28 degrees. I'm going to add to it the coefficient of static friction. Static is the larger one. It's going to be 0.4, 0.40 times the force of 13 newtons times the cosine of the angle 28 degrees. And I have to divide all of that by 9.8 meters per second. There's my expression for mass once I've substituted my numbers in for it. And for problem number 56, I get 1.1 kilograms once I put all of that into my calculator.